Introduction to GHASH Mathematics. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will work with the actual mathematics used in GHASH for AES-GCM. This means working in the Galois Field GF of 2 to the 128th power, using 128-bit numbers and the correct irreducible polynomial. We will start from the absolute basics, explaining what bits are, what XOR means at the bit level, and what polynomials are. Then we will build up to the full GHASH algorithm with complete examples. We will use hexadecimal notation to represent large numbers compactly. Each hexadecimal digit represents 4 bits, so a 128-bit number is represented by 32 hexadecimal digits. By the end, you will understand every step of how GHASH produces authentication tags. Understanding bits and binary. Before we can understand GHASH, we need to understand bits. A bit is the fundamental unit of information in computing. It can have only 2 values, 0 or 1. You can think of a bit as an on-off switch, a true-false value, or a yes-no answer. Multiple bits are combined to represent larger numbers. For example, 8 bits make a byte. In binary notation, we write numbers using only zeros and ones. The rightmost bit represents the value 1. The next bit to the left represents 2, then 4, then 8, and so on, each position being double the previous. For example, the binary number 1011 means 18, 04s, 12, and 11, which equals 8 plus 2 plus 1 equals 11 in our normal decimal system. In GHASH, we work with 128 bits at a time, which can represent numbers from 0 up to 2 to the 128th power minus 1, an astronomically large number. To make these large binary numbers easier to read, we use hexadecimal notation. Hexadecimal uses 16 digits, 0 through 9, then A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. Each hex digit represents exactly 4 bits, so 32 hex digits represent 128 bits. Let's look at a concrete example. Take the hexadecimal value 0xAB. The A represents the value 10, which in binary is 1010. The B represents the value 11, which in binary is 1011. So 0xAB in binary is beginning with 10 ending with 11. To convert this to decimal, we calculate 1 times 128 plus 0 times 64 plus 1 times 32 plus 0 times 16 plus 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which equals 128 plus 32 plus 8 plus 2 plus 1, which equals 171 in decimal. This shows how hexadecimal provides a compact way to represent binary numbers, making it much easier to work with large values like the 128-bit numbers used in GHASH. What is XOR at the bit level? XOR stands for exclusive OR, and it's a fundamental operation in cryptography. XOR operates on individual bits according to a simple rule. If the 2 input bits are the same, the output is 0. If the 2 input bits are different, the output is 1. Let's see this in detail. 0 XOR 0 equals 0 because both bits are the same. 0 XOR 1 equals 1 because the bits are different. 1 XOR 0 equals 1 because the bits are different. 1 XOR 1 equals 0 because both bits are the same. When we XOR 2 multi-bit numbers, we XOR each corresponding pair of bits independently. For example, to XOR the binary numbers 1010 and 0110, we go bit by bit from right to left. Position 0. 0 XOR 0 equals 0. Position 1. 1 XOR 1 equals 0. Position 2. 0 XOR 1 equals 1. Position 3. 1 XOR 0 equals 1. The result is 1100. XOR has several important properties. It's commutative, meaning A XOR B equals B XOR A. It's associative, meaning A XOR B XOR C equals A XOR B XOR C, and it's self-inverse, meaning A XOR B XOR B equals A. This last property is crucial. XORing with the same value twice gets you back where you started. In GHASH, we use XOR as our addition operation in the Galois field. What are polynomials? The polynomial is $math_rm GHASH with binary coefficients, meaning each coefficient is either 0 or 1. For example, x cubed plus x plus 1 is a polynomial with binary coefficients. The powers of x correspond to bit positions in our binary numbers. If we have the binary number 1011, we can represent it as the polynomial x cubed plus 0 times x squared plus x plus 1. The rightmost bit is the constant term. The next bit is the coefficient of x. The next is x squared, and so on. This polynomial representation allows us to multiply binary numbers using polynomial multiplication rules. When we multiply two polynomials, we multiply each term of one polynomial by each term of the other, and add up the results. In our case, addition means XOR. This polynomial view is fundamental to understanding how $math_rm GHASH performs multiplication in the Galois field. The Galois field GF 2 to the power of 128. GHASH operates in a mathematical structure called a Galois field, specifically GF of 2 to the 128th power. A field is a set of numbers with addition and multiplication operations that follow certain rules. In GF of 2 to the 128th power, there are exactly 2 to the 128th power elements, which is approximately 3.4 times 10 to the 38th power. Each element is a 128-bit value. The addition operation in this field is XOR, which we just learned about. The multiplication operation is polynomial multiplication followed by modular reduction. The field is defined by an irreducible polynomial, which we will discuss in detail shortly. What makes this a field is that it is closed under addition and multiplication. This means that when you add or multiply any two elements in the field, you always get another element in the field. There are no overflows or special cases. Every non-zero element has a multiplicative inverse, and all the usual algebraic rules, such as the distributive property, hold. This mathematical structure is perfect for cryptography because operations are efficient on computers, and the field has strong mathematical properties that provide security. The irreducible polynomial. The irreducible polynomial is the key component that defines our Galois field. For GF of 2 to the 128th power used in AES-GCM, the irreducible polynomial is R of x equals x to the 128th power plus x to the 7th power plus x squared plus x plus 1. An irreducible polynomial is one that cannot be factored into smaller polynomials over GF of 2. Similar to how a prime number cannot be factored into smaller integers. This particular polynomial was chosen for AES-GCM because it is irreducible and has properties that make reduction efficient. If we were to write this polynomial in binary with all bits, it would have bit 128 set, then bits 7, 2, 1, and 0 set, with all other bits 0. That is beginning with 10 ending with 111 with 1200 zeros in the middle. However, since we work with 128-bit values, we represent just the lower 128 bits for reduction. The representation is 0x beginning with 00 ending with 87 in hexadecimal. The hex value 87 is beginning with 10 ending with 111 in binary, showing bits 7, 2, 1, and 0. During modular reduction, whenever our multiplication result has bits set at position 128 or higher, we use this reduction polynomial to bring the result back to 128 bits. The sparse nature of this polynomial, with only 5 bits set, makes the reduction operation very efficient. XOR with 128-bit numbers. Now let's see how XOR works with actual 128-bit numbers represented in hexadecimal. Take A equals 0x beginning with 01 and ending with EF. Take B equals 0x beginning with FE and ending with 10. To compute A XOR B, we can work hex digit by digit, but it's important to understand what's happening at the bit level. Let's focus on a few bytes to see the details. The first byte of A is 0x01, which is 00000001 in binary. The first byte of B is 0xFE, which is 11111110 in binary. XOR-ing these bit by bit. 0 XOR 1 equals 1, 0 XOR 1 equals 1, and so on. The result is 11111111, which is 0xFF. Let's do another byte. The second byte of A is 0x23, which is 00100011 in binary. The second byte of B is 0xDC, which is 11011100 in binary. XOR-ing. 0 XOR 1 equals 1, 0 XOR 1 equals 1, 1 XOR 0 equals 1, and so on. The result is 11111111, which is 0xFF. We continue this for all 16 bytes. The complete result is 0x beginning with FF and ending with FF, which is all 128 bits set to 1. Polynomial representation in detail. Every 128-bit value can be viewed as a polynomial with binary coefficients. Let's examine this in detail. Take the hexadecimal value 0x beginning with 00 ending with 87. To see the polynomial, we first convert to binary. The hex digit 8 is 1000 in binary, and 7 is 0111 in binary, so 87 is 10000111. This means bits 7, 2, 1, and 0 are set, with all other bits 0. In polynomial form, this is x to the 7th power plus x squared plus x plus 1. Each set bit contributes a term with its corresponding power of x. Bit 0 contributes 1, bit 1 contributes x, bit 2 contributes x squared, and so on. Another example. 0x beginning with 00 ending with 03 is 00000011 in the lowest byte, so bits 1 and 0 are set. This represents x plus 1. The value 0x beginning with 80 ending with 00 has only the highest bit set, bit 127, representing x to the 127th power. This representation is powerful because it lets us use polynomial algebra to multiply numbers. When we multiply polynomials, we use the distributive property and combine like terms. In our binary case, combining like terms means XOR-ing the coefficients. Polynomial multiplication example. Let's multiply two small polynomials to see how it works. Take A equals x plus 1, which is beginning with 0x00 ending with 03. Take B equals x, which is beginning with 0x00 ending with 02. To multiply these polynomials, we use the distributive property. The polynomial x plus 1 times x equals x times x plus 1 times x. This gives us x squared plus x. Now let's find the hexadecimal representation. X squared means bit 2 is set, which is beginning with 0x00 ending with 04. X means bit 1 is set, which is beginning with 0x00 ending with 02. We XOR these together. 0x04 XOR 0x02 equals 0x06. So the result is beginning with 0x00 ending with 06. Let's verify by looking at the bits. 0x06 is binary 0110, which is x squared plus x, correct? For larger polynomials, the process is the same but involves more terms. We multiply every term of one polynomial by every term of the other, which generates many intermediate products. We then combine all these products by XOR-ing their coefficients. The challenge is that when multiplying two 128-bit polynomials, the result can have terms up to x to the 255th power, requiring up to 256 bits. That's where modular reduction comes in. Polynomial multiplication mathematics. Let's dive deeper into the mathematics of polynomial multiplication with detailed examples. Polynomial multiplication uses the distributive property. We multiply each term of the first polynomial by each term of the second polynomial, then add all the results. In regular algebra, if we multiply x plus 2 times x plus 3, we get x times x, which is x squared, x times 3, which is 3x, 2 times x, which is 2x, and 2 times 3, which is 6. Adding these gives x squared plus 5x plus 6. In binary polynomial multiplication for GHASH, the process is identical except coefficients are only 0 or 1, and addition as XOR lets work through x squared plus x plus 1 times x plus 1. We multiply each term. X squared times x equals x cubed. X squared times 1 equals x squared. X times x equals x squared. X times 1 equals x. 1 times x equals x. 1 times 1 equals 1. Now we collect like terms. X cubed appears once, so its coefficient is 1. X squared appears twice, so its coefficient is 1 XOR 1, which equals 0, meaning it cancels out. X appears twice, so it also cancels out with coefficient 0. The constant 1 appears once with coefficient 1. The final result is x cubed plus 1. This cancellation property is crucial in binary polynomial arithmetic. When a term appears an even number of times, it disappears. When it appears an odd number of times, it remains. This is because in GF of 2, 1 plus 1 equals 0. Let's do another example with larger polynomials to see the full process in action. Modular reduction explained. After multiplying two 128-bit polynomials, we get a result up to 256 bits. To keep our result in GF of 2 to the 128th power, we must reduce it modulo the irreducible polynomial. The reduction process works as follows. We examine the result from the highest bit down to bit 128. For each bit position k that is set, where k is greater than or equal to 128, we need to eliminate that bit. We do this by XORing with the irreducible polynomial shifted appropriately. Let me explain why this shifting works. The irreducible polynomial is r of x equals x to the 128th plus x to the 7th plus x squared plus x plus 1. In the field, this means x to the 128th equals x to the 7th plus x squared plus x plus 1. Therefore, if we have x to the k, where k is at least 128, we can write x to the k as x to the k minus 128 times x to the 128th. This then equals x to the k minus 128 times the quantity x to the 7th plus x squared plus x plus 1. Distributing this gives us x to the k minus 121 plus x to the k minus 126 plus x to the k minus 127 plus x to the k minus 128. Let's see a concrete example. Suppose we need to eliminate bit 130. We have x to the 130th set in our result. Now x to the 130th equals x squared times x to the 128th. By substituting x to the 128th with x to the 7th plus x squared plus x plus 1, we get x squared times the quantity x to the 7th plus x squared plus x plus 1. Distributing x squared gives us x to the 9th plus x to the 4th plus x cubed plus x squared. So, when we XOR our result with x to the 130th plus x to the 9th plus x to the 4th plus x cubed plus x squared, the x to the 130th terms cancel each other out. This leaves us with the lower terms. This eliminates bit 130. We repeat this process for each bit from 255 down to 128, working from high to low. Each reduction step eliminates one high bit. After processing all bits at position 128 and above, we're left with only bits 0 through 127 set, giving us our final 128-bit result. The efficiency of this process depends on the sparse nature of the reduction polynomial. With only 5 bits set in the irreducible polynomial, each reduction step is very fast. Complete multiplication and reduction example. Let us work through a complete multiplication with reduction using small values. We will multiply a, which equals 0x beginning with 0, 0 ending with 0, 3, representing x plus 1, by b, which equals 0x beginning with 0, 0 ending with 8, 7, representing x to the 7th plus x squared plus x plus 1. First, consider the polynomial multiplication. We have x plus 1 times x to the 7th plus x squared plus x plus 1. Using the distributive property, x times x to the 7th plus x squared plus x plus 1 equals x to the 8th plus x cubed plus x squared plus x, and 1 times x to the 7th plus x squared plus x plus 1 equals x to the 7th plus x squared plus x plus 1. Now we add these with XOR. We have x to the 8th appears once, x to the 7th appears once, x cubed appears once, x squared appears twice, so it cancels. X appears twice, so it cancels. 1 appears once. The result is x to the 8th plus x to the 7th plus x cubed plus 1. In hex, x to the 8th is bit 8, which is 0x100. X to the 7th is bit 7, which is 0x80. X cubed is bit 3, which is 0x08. 1 is bit 0, which is 0x01. Combining these, 0x100 plus 0x80 plus 0x08 plus 0x01 equals 0x189. Now we check if reduction is needed. The result 0x189 is 9 bits, fitting in bits 0 through 8. Since bit 8 is less than 128, no reduction is needed. The final result is 0x beginning with 0, 0 ending with 189. Reduction example with overflow above x to the power of 128. Now let's see a more detailed reduction example where the multiplication result has bits set well above position 128. This shows the complete reduction process in action. Take a equals beginning with 0, 0 and ending with 0, 0, which is x to the 120th power. Take b equals beginning with 0, 0 and ending with 2, 1, which is x to the 10th plus x to the 5th plus 1. First, polynomial multiplication. X to the 120th times x to the 10th plus x to the 5th plus 1 equals x to the 130th plus x to the 125th plus x to the 120th. This result has bits 130, 125, and 120 set. Bit 130 exceeds our 128-bit field, so we must reduce. The reduction process works from the highest bit down. Bit 130 is the highest bit set. To eliminate it, we XOR with the reduction polynomial shifted by 130 minus 128 equals 2 positions. The reduction polynomial is x to the 128th plus x to the 7th plus x squared plus x plus 1. Shifting this left by 2 positions gives us x to the 130th plus x to the 9th plus x to the 4th plus x cubed plus x squared. Now we XOR our current result with this shifted polynomial. X to the 130th plus x to the 125th plus x to the 120th XOR x to the 130th plus x to the 9th plus x to the 4th plus x cubed plus x squared. The x to the 130th terms cancel each other out. The new result is x to the 125th plus x to the 120th plus x to the 9th plus x to the 4th plus x cubed plus x squared. Now we check again. The highest bit is 125, which is less than 128, so we're done. No more reduction needed. The final result is x to the 125th plus x to the 120th plus x to the 9th plus x to the 4th plus x cubed plus x squared. This demonstrates the complete reduction process when we have overflow above bit 128. Complete Galois field multiplication with reduction. Now let's see a complete example that actually requires reduction. This demonstrates the full Galois field multiplication operation used in GHASH. We'll multiply two larger values. Take A equals beginning with 80 ending with 00, which is x to the 127th power. Take B equals beginning with 00 ending with 03, which is x plus 1. First, polynomial multiplication. X to the 127th times x plus 1 equals x to the 128th plus x to the 127th. This is a 129-bit result with bits 128 and 127 set. In hexadecimal, if we could represent 129 bits, this would be bit 128 and bit 127 set. Now we must reduce because bit 128 is set, which exceeds our 128-bit field. The reduction polynomial is x to the 128th plus x to the 7th plus x squared plus x plus 1. When bit 128 is set in our result, we XOR with the reduction polynomial to cancel it. X to the 128th XOR x to the 128th plus x to the 7th plus x squared plus x plus 1 gives us x to the 7th plus x squared plus x plus 1. But we also still have x to the 127th from our original result. So the complete reduced result is x to the 127th plus x to the 7th plus x squared plus x plus 1. In hexadecimal, this is beginning with 80 ending with 87. Let me verify. X to the 127th is bit 127, which is beginning with 80 ending with 00. X to the 7th plus x squared plus x plus 1 is 0x87. XO ring these gives beginning with 80 ending with 87. This is our final result after Galois field multiplication and reduction. The hash subkey H. In GHASH, the hash subkey H is a secret 128-bit value that serves as the cryptographic key for the authentication function. In a real AES-GCM implementation, H is derived from the main encryption key. Specifically, H is computed by encrypting a block of 128 0 bits using AES with your secret key. H equals AES encrypt with key K of 0 to the 128th power. This makes H depend entirely on the secret key K. Someone who does not know K cannot compute H. For our examples, we will use a specific value of H to demonstrate the calculations. Let us set H equal to beginning with 01 ending with EF. This is a 128-bit value represented as 32 hexadecimal digits. In polynomial form, H represents a polynomial with many terms. Looking at just the lowest byte, beginning with EF ending with EF is beginning with 11 ending with 11 in binary. So bits 7, 6, 5, 3, 2, 1, and 0 are set, giving us terms x to the 7th, x to the 6th, x to the 5th, x cubed, x squared, x, and 1. The full polynomial has terms scattered throughout all 128-bit positions. Every GHASH operation involves multiplying data by H or powers of H. The security of GHASH depends entirely on H being secret. An attacker who learns H can forge authentication tags. Therefore, H must be kept as secret as the encryption key itself. The GHASH iteration formula. The core of GHASH is an iterative process that cryptographically accumulates message blocks. We maintain a running accumulator Y, which starts at 0. For each 128-bit message block X subscript I, we compute a new accumulator value using the formula Y subscript I equals the quantity Y subscript I minus 1 XOR X subscript I, all multiplied by H in the Galois Field GF of 2 to the 128th power. Let's break this down step by step. First, we take the current accumulator value y subscript I-1. We XOR it with the new message block x subscript I. This XOR operation combines the accumulator with new data. Then we multiply the result by h using polynomial multiplication. This multiplication is done in GF of 2 to the 128th power, which means we multiply the polynomials and then reduce the result modulo the irreducible polynomial to keep it at 128 bits. The result becomes our new accumulator y subscript I. We repeat this process for every message block. This formula has an important mathematical property. If we expand the recursion for multiple blocks, we can express the final result as y equals x1 times h to the n plus x2 times h to the n minus 1 plus plus xn times h. This shows that each message block is multiplied by a different power of h depending on its position in the message. This position-dependent weighting is crucial for security because it means an attacker cannot rearrange blocks or substitute blocks without changing the final authentication value. Processing the first block. Let's work through processing the first message block in detail. Suppose our first message block is x1, equal to the hexadecimal value beginning with 0xFF and ending with FF, which has all 128 bits set to 1. Our hash key is h, equal to the hexadecimal value beginning with 0x01 and ending with DEF. The initial accumulator is y0, equal to the hexadecimal value beginning with 0x00 and ending with 00, which is all zeros. Step 1. Compute y0 XOR x1. Since y0 is all zeros, XORing with x1 simply gives us x1. Each bit of y0 is 0, and we XOR it with the corresponding bit of x1. 0 XOR 0 equals 0, and 0 XOR 1 equals 1. Since all bits of x1 are 1, the result is the hexadecimal value beginning with 0xFF and ending with FF. Step 2. Multiply by h. We need to compute the hexadecimal value beginning with 0xFF and ending with FF, multiplied by the hexadecimal value beginning with 0x01 and ending with DEF, in GF of 2 to the 128th power. This is a complex operation. In polynomial terms, the hexadecimal value beginning with 0xFF and ending with FF represents the polynomial with all 128 terms. X to the 127, plus x to the 126, plus plus x plus 1. Multiplying by h means we are adding shifted versions of h for every bit position. The calculation involves polynomial multiplication, generating up to 256-bit intermediate results, followed by repeated reductions using the irreducible polynomial. The final result after all reductions might be something like y1, equal to the hexadecimal value beginning with 0xd5 and ending with 4b2. This is our accumulator value after processing the first block. Processing the second block. Now let's process a second message block. Suppose x2 equals 0x, beginning with 00 ending with FF. This has a specific pattern of bytes. Our current accumulator is y1 equals 0x, beginning with D5 ending with B2, from the previous step. Step 1. Compute y1 XOR x2. We XOR each byte. The first byte, 0xD5 XOR 0x00. In binary, 0xD5 is 11010101 and 0x00 is 00000000. XO ring bit by bit. 1 XOR 0 equals 1, 1 XOR 0 equals 1, and so on. The result is 11010101, which is 0xD5. The second byte, 0xC2 XOR 0x11. In binary, 0xC2 is 11000010 and 0x11 is 00010001. XO ring. 1 XOR 0 equals 1, 1 XOR 0 equals 1. 0 XOR 0 equals 0. 0 XOR 1 equals 1, and so on. The result is 11010011, which is 0xD3. We continue for all 16 bytes. The complete result is Y1 XOR X2 equals 0x, beginning with D5 ending with 5D. Step 2. Multiply by H. We compute 0x, beginning with D5 ending with 5D, times 0x, beginning with 01 ending with EF. This involves treating both as polynomials, multiplying all terms, and reducing. The result after full polynomial multiplication and reduction might be Y2 equals 0x, beginning with 3f ending with 3f. This accumulator now cryptographically depends on both x1 and x2. Processing the third block. Let's process one more message block. Suppose x3 equals beginning with 0x00 ending with 01, which is just the value 1 with bit 0 set. Our accumulator is y2 equals beginning with 0x3f ending with 3f. Step 1. Compute y2 XOR x3. Since x3 has only the lowest bit set, this XOR operation flips only the lowest bit of y2. Let's look at the lowest byte of y2, which is 0x3f in binary. 0x3f is 00111111. XOR-ing with 0x01, which is 00000001. We get the lowest bit, 1 XOR1, equals 0, and all other bits remain unchanged. The result is 00111110, which is 0x3e. So y2 XOR x3 equals beginning with 0x3f ending with 3e. Step 2. Multiply by H. We compute beginning with 0x3f ending with 3e times beginning with 0x01 ending with ef in GF of 2 to the 128th power. This again requires full polynomial multiplication and reduction. The result might be y3 equals beginning with 0x7e ending with 7e. This y3 value now depends on all three message blocks x1, x2, and x3. The recursive structure ensures that changing any bit of any previous block completely changes the final accumulator value. This provides the tamper detection property we need for authentication. Adding linked information. After processing all message blocks, GHASH adds one final block containing linked information. This linked block is crucial for security because it prevents certain attacks. The linked block L is a 128-bit value with a specific structure. The upper 64 bits contain the linked-in bits of the additional authenticated data, or AAD. The lower 64 bits contain the linked-in bits of the ciphertext. In our example, suppose we had no AAD, so the AAD length is 0. Our ciphertext consists of 3 blocks, each 128 bits, for a total of 384 bits. In hexadecimal, 384 is 0x180. So our linked block L equals beginning with 00 and ending with 180. The upper 64 bits are all zeros for the AAD length, and the lower 64 bits are beginning with 00 and ending with 180 for the ciphertext length. Step 1. Compute Y3 XOR L. We have Y3 equals beginning with 7e and ending with C7e and L equals beginning with 00 and ending with 180. When XOR-ing these values, most bytes remain unchanged because the corresponding bytes of L are 0. Only the bytes where L has non-zero values change. The result is Y3 XOR L equals beginning with 7e and ending with DFE. Step 2. Multiply by H. We compute beginning with 7e and ending with DFE times H. The result after multiplication and reduction is the final GHASH output S equals beginning with a 1 and ending with EF01. This S value depends on all message blocks plus the length information. generating the final authentication tag. The GHASH output S is not quite the final authentication tag used in AES-GCM. There's one more step that adds an additional layer of security. In GCM mode, we use counter mode encryption. We have a nonce, which is a number used once, and we construct an initial counter from it. This initial counter, often denoted J0, is encrypted using AES with the same key K that was used to derive H. Let's call this encrypted counter value E, so E equals AES encrypt with key K of J0. For our example, suppose this encrypted counter value is E equals beginning with 9F ending with C0. The final authentication tag T is computed by XO ring S with E. T equals S XOR E. We have S equals beginning with a 1 ending with 01 and E equals beginning with 9F ending with C0. Let's XOR them byte by byte. First byte 0xA1 XOR 0x9F in binary. 0xA1 is beginning with 10 ending with 01 and 0x9F is beginning with 10 ending with 11. XO ring bit by bit gives beginning with 00 ending with 10, which is 0x3E second byte. 0xB2 XOR 0x8E gives 0x3C. We continue for all 16 bytes. The final result is T equals beginning with 3E ending with C1. This T is our authentication tag. It's sent along with the encrypted message to the recipient. The XOR with E binds the authentication to the specific nonce being used, preventing certain replay and forgery attacks. Complete example summary. Let's summarize the complete calculation from start to finish with all values. Hash key H equals 0x, beginning with 01, ending with EF. This is derived from the encryption key K as H equals AES encrypt of 0 to the 128. Message blocks. X1 equals 0x, beginning with FF, ending with FFX2 equals 0x, beginning with 00, ending with FFX3 equals 0x, beginning with 00, ending with 01. Length block. L equals 0x, beginning with 00, ending with 80. GHASH iteration. Y0 equals 0x, beginning with 00, ending with 00. Y1 equals the quantity Y0x or X1 multiplied by H equals 0x, beginning with D5, ending with B2. Y2 equals the quantity Y1x or X2 multiplied by H equals 0x, beginning with 3F, ending with 3F. Y3 equals the quantity Y2x or X3 multiplied by H equals 0x, beginning with 7E, ending with 7E. Y4 equals S equals the quantity Y3x or L multiplied by H equals 0x, beginning with A1, ending with 01. Final tag computation. Encrypted counter E equals 0x, beginning with 9F, ending with C0. Authentication tag T equals SX or E equals 0x, beginning with 3E, ending with C1. This tag T authenticates our 3-block message and the length information, all bound together by the secret H and the nonce-derived E. Verification process. When the recipient receives the message, they perform verification to ensure the message has not been tampered with. The recipient receives the encrypted message blocks X1, X2, X3, and the authentication tag T, which equals, beginning with 3E and ending with C1. The recipient has the same hash key H because they share the encryption key K. They perform the exact same GHASH calculation. They compute Y0 equals 0, which represents all zeros. Y1 equals X1 times H, which equals, beginning with D5 and ending with B2. Y2 equals the quantity Y1 XOR X2 times H, which equals, beginning with 3F and ending with BF. Y3 equals the quantity Y2 XOR X3 times H, which equals, beginning with 7E and ending with 7E. They compute the length block L, which equals, beginning with 00 and ending with 80, based on the received data sizes. S prime equals the quantity Y3 XOR L times H, which equals, beginning with a 1 and ending with 0, 1. They compute their own encrypted counter value E, which equals, beginning with 9F and ending with CO, using the same nonce and key. They compute T prime equals S prime XOR E, which equals, beginning with 3E and ending with C1. Now they compare. T prime equals, beginning with 3E and ending with C1. The received T equals, beginning with 3E and ending with C1. They match exactly. All 128 bits are identical. This means the message is authentic and has not been modified. If even a single bit anywhere in any message block had been changed, the recomputed T prime would be completely different from the received T, and the recipient would reject the message. Security analysis and forgery resistance. The security of GHASH comes from the mathematical structure of polynomial evaluation over a Galois field. Let's understand why an attacker cannot forge authentication tags. Suppose an attacker wants to create different message blocks x1 prime, x2 prime, x3 prime that produce the same GHASH output as the original blocks x1, x2, x3. Mathematically, the attacker needs x1 prime times h cubed plus x2 prime times h squared plus x3 prime times h to equal x1 times h cubed plus x2 times h squared plus x3 times h. Rearranging this equation, the quantity x1 minus x1 prime times h cubed plus the quantity x2 minus x2 prime times h squared plus the quantity x3 minus x3 prime times h equals 0. This is a polynomial equation in the variable h if the attacker's message is actually different from the original, meaning at least one of x1 prime, x2 prime, or x3 prime differs from its original value, then this is a non-zero polynomial. A fundamental theorem from algebra states that a non-zero polynomial of degree d has at most d roots. Our polynomial has degree at most 3. So it has at most 3 solutions for h, but h is a secret value chosen from 2 to the 128th power possible values, which is approximately 3.4 times 10 to the 38th power. The probability that the attacker's fake message happens to satisfy the equation with the actual secret h is at most 3 divided by 2 to the 128th power. This is approximately 8.8 times 10 to the negative 39, an astronomically small number. For comparison, the probability of winning a typical lottery is about 10 to the negative 8. The probability of successful forgery is 31 orders of magnitude smaller. This makes forgery computationally infeasible. Implementation and hardware acceleration. Implementing GHASH efficiently requires careful attention to the multiplication and reduction operations. The naive bit-by-bit approach is slow, so real implementations use optimizations. Modern processors have special instructions designed specifically for the polynomial multiplication needed in GHASH on Intel and AMD processors. There is an instruction called PCLMULQDQ, which stands for carry less multiplication quadword. This instruction performs 64-bit polynomial multiplication in hardware in just a few clock cycles. To multiply two 128-bit values, we treat each as two 64-bit halves and use the PCLMULQDQ instruction 4 times, then combine the results. This is based on Karatsuba's algorithm, which can reduce 4 multiplications to 3 with some additional additions. On ARM processors, there is a similar instruction called PMULL, which stands for polynomial multiply long. It provides equivalent functionality for efficient GF of 2 arithmetic. With these hardware instructions, GHASH can achieve speeds of 5 to 10 gigabits per second on a single CPU core. For platforms without these special instructions, table-based methods can be used. We precompute tables of products of H with various values, then look up and combine results. The implementation must also be constant time, meaning execution time does not depend on the data values. This prevents timing side-channel attacks where an attacker measures execution time to learn information about the secret H hardware instructions naturally provide constant time operation. Mathematical summary and conclusion. Let's summarize all the mathematical components of GHASH in GF of 2 to the 128th power. The GF of 2 to the 128th power field contains 2 to the 128th power elements, each represented as a 128-bit value, or equivalently, as a polynomial of degree at most 127 with binary coefficients. Addition is performed using XOR, the bitwise exclusive OR operation. For two 128-bit values, we XOR each of the 128 corresponding bit pairs. Multiplication is performed by treating values as polynomials, multiplying them to get up to a 256-bit result, then reducing modulo the irreducible polynomial. The irreducible polynomial R of x equals x to the 128th plus x to the 7th plus x squared plus x plus 1. For reduction, we use the representation 0x87 in the lowest byte. For GHASH iteration, y subscript I equals the quantity y subscript I minus 1 XOR x subscript I, all multiplied by h in the field. The hash subkey h is derived from the encryption key as h equals AES encrypt of 0 to the 128th. The linked block encodes AAD and ciphertext lengths in bits. The final tag T equals GHASH output XOR encrypted counter. For security, forging requires solving polynomial equations in the secret H, with a success probability at most d divided by 2 to the 128th, where d is the number of message blocks. This is negligible for practical D for implementation. Hardware instructions like PCLMULQDQ or PMULL are used for efficient polynomial multiplication, achieving multi-gigabit speeds. This mathematical structure provides both strong security guarantees and efficient implementation, making GHASH ideal for authenticated encryption in high-speed applications. Thank you for your attendance. Please consider subscribing to the channel.